But with that said, I want to dive into the topic of today, which is really a continuation of Mondays, which is tracing back our chemical origins, and if understanding knowing what we know, can we say anything interesting about the likelihood of there being life elsewhere? So that's going to be the topic for today. So I'm going to try to bring together basically three different things. One is the prevalence of exoplanets, so planets around other stars. The other is what we can know about their composition, so what they are made of, like what we can infer, mainly from actually what we know about how they form, what we can infer about what these planets are like. And then the third thing, what we understand about the origins of life here on Earth. And what I think that yesterday, Monday, there was a connection that was actually pretty clear, but I think mostly sort of a positive one, if you can put it like that, with theology. I think when we are considering life elsewhere and extraterrestrial life, there is at least a potential for some tension. So we're still going to have, now when we think about life elsewhere, exoplanets elsewhere, we're still going to have to think about what cosmology we live in and what that is telling us about God as a creator, about our sort of combined scientific and theological understanding of creation. So that's still going to be there, sort of continuing from Monday. And when we think about life that is sort of bacterial, so the origins of life here and elsewhere, there are going to be some metaphysical tension, and this is not just for religious people, and how you go from having chemistry to biology. It is not really obvious how you do that in a sort of philosophically coherent way. I mean, Thomas Nagel, famously put this out a few years ago and was, not adored, let's say, by the secular society for questioning that this is an easy transition to make, even conceptually, from from chemistry to biology. But I think for Catholics, Christians in general, but there are actually a couple of extra sort of items for Catholics, where sort of the potential real tension comes in is when we're considering the possibility of extraterrestrial rational life or intelligent life. And the tension there is with the incarnation, which is this very specific incarnation into our kind of rational being, right? So we'll come back to that, but to put it in other words, I mean, if there are two sort of threats from extraterrestrial intelligent life to our sort of self-understanding, to our theology, it is one, it's sort of to our specialness. Are we really, the crown of creation through which potentially this 14 billion light year kind of universe revolves around? I mean, that is still a possibility. I mean, if you talk about, on one hand, seeing the whole cosmos make you feel insignificant, but what if it's all there for us? I mean, that would be pretty cool. Actually, I hope it isn't, but I mean, it could be that it's actually shouldn't make you feel insignificant. But other one is how, whether it's compatible with church teachings and with scriptures, especially on the incarnation, but also for us Catholics, also when it comes to our role on Mary. But let's start with the, uncontroversial part. So I want to give you a very brief primer about planets around other stars and how we know that they are there. So what we do know, to start with the conclusion, is that most stars, if you look up at the sky, the stars you see have planets around them. The majority of stars do have their own solar systems. Now, this is actually, again, changes our cosmology a bit. I mean, if you think about it, we no longer just have, we moved away from the lamps. We moved away from, I guess, the angels moving the stars, which was one of the theories that even Galileo had said that was a possibility. And we moved away from this mechanical universe, that they're eternal and they're just moving on the sky. And Monday went into this much more dynamic cosmos, right, where this come into being and die over time. But now we're sort of changing it again, where each of them is their own worlds. They're not just these cold lights far, far away, but they're actually in some sense cozier solar systems, like homes like our own, potentially. Now, conceptually, the easiest way to detect planets would be to do it as we do it in our own solar system. That is to just look at them. So astronomers would call this direct imaging. You take an image directly. This works very well in the solar system. This is one of many beautiful images of one of our local planets, Saturn. Now, there are exoplanets that are detected like this way, and I'm going to show you the most famous example, which is this one. So here you have blocked out the star, because otherwise the light from the star would overpower seeing any of the planets, which are much, much dimmer. I mean, when you're trying to look at the sky and you have the sun out, like if you block the sun with your hand, you actually see things more clearly around it. And that is exactly what we're doing here with the star. And then you see that there are these like 4 dots. And these dots have been followed for many years. You can see the timestamp down here. So this was first discovered in 2009, so a decade ago. And people have gone back every year to take new pictures. And what they see when they put it together into a little movie is this. So you actually do see these planets moving around, which is pretty fantastic. Now, there are a few more like this, but it's really like a handful. And the reason for that is that the planets have to be pretty far away for you to be able to separate their light from the stars. And they have to be very bright, so they have to be Jupiter size. Those are the only systems. Please.
Do you know the name or the identification?
So it's HR 8799. One of, many, not really, I don't know, cool names. But it is a beautiful system, but these are very rare. Instead, how most planets are detected is by using a more indirect technique, which is called the transit technique. So this is just an animation of how this works, but what you will see is that we use the fact that if we have the right geometry, so we have we are here, the star is here, and the planet is in the same plane. As the planet orbits the star, it will then and then block out some light of the star. So that is the transit method, and here's just an animation of what that looks like. So you will see the light curve down here that the astronomers are actually measuring. Now, you can't learn as much from these light curves as you can from an image, but you can learn quite a lot of things. The depth of this light curve will tell you how big the star is. The bigger the star, the more light, or the bigger the planet, the more light it blocks out. The duration will tell you how fast the planet is moving. And because of Kepler's law, we know that the further away you are from the star, the slower you are moving. So you can actually use the duration here to tell how far the planet is from the star. And if you combine this kind of measurements with, if you have multiple planets in the system, then each planet sort of tugs a little bit on one another. So you see small shifts in this curve, and you can use that to measure the mass. So in the perfect systems, you can actually learn a lot about the planets that you see. And the result is that we have this zoo of planets, of all kinds of sizes, masses, distances from the star. When people started looking for exoplanets, they expected to see sort of versions of our solar system. That is not what we're seeing. We're seeing Jupiters that are close to their star. We're seeing Jupiters that are out where Pluto is sitting. We're seeing Neptune-like planets that are where Earth is sitting. It's all we're seeing all kinds of sizes, also these sort of in-between sizes that we don't really have in the solar system, where we sort of jump from Earth-sized to ice giants. In extrasolar system, you're also seeing everything in between. And we now have enough data to say, what is the typical planet in our galaxy? And if we go down here, we don't really have enough data to the smallest planets to say how many there are. The smaller the planet, the smaller dip they make, so they're more difficult to detect. But even with sort of compensating for that difficulty, we now have enough data to say that the most common planets in the galaxy are these in-between planets that we actually do not have in the solar system. So they're either called super-Earths or mini-Neptunes, dependent on if people think they're icy or rocky. But they are these in-between planets. So what we can say already from this is that we are not unique in the sense that we have a solar system. So these solar systems are incredibly common. But we are not the typical system. The kind of hierarchy that we have in our solar system with sort of a few small planets and then a few big ones, we haven't really seen exactly that yet. We have like one that's fairly close, but this is not a common structure of a solar system. And people have speculated that maybe the kind of planetary system we live in is especially good for the origins of life. But we'll come back to it. We actually don't know what are the required ingredients for an origins of life. But there are a couple of things about our solar system that seems to have been favorable to having a sort of very stable kind of geometry. You have the rocky planets at the right place. You don't have any big planets swooping in and disturbing them and things like that. You don't have icy planets coming in and sitting where the Earth ought to be. But even with that sort of big caveat, we do have some of these more Earth-sized planets. And a subset of those are sitting roughly where the Earth is sitting. If you look at stars like the Sun, on the order of a couple of % of them do have an Earth-like planet in the sort of temperate zone where that the Earth is sitting in. And if we are not limiting ourselves to Sun-like stars, but ask ourselves, okay, if we have any kind of star, we don't know how important the star is for life. Maybe any sort of light will do. So even if it's a smaller star or a bigger star, doesn't really matter. How many planets do we know that do seem to have the right conditions for life? And the ones where we are fairly certain that are sitting in the temperate zone where water can be liquid are the ones listed here in sort of order of how close they are. You can see that the closest one is really very close. Proxima is called Proxima because it is the most proximate star. So our nearest neighbor has a planet that could be habitable. The problem with many of these planets is that they're sitting around so-called M-dwarfs. These are very small stars. And if you're sitting around a very small star, to be warm enough, you have to be very close to it. So astronomers like talking about the habitable or temperate zone. Again, this is a zone which is warm enough for water to be liquid, but not so warm that water sublimates into vapor. And where this zone is depends on what kind of star you have. So we are used to thinking about it as being one astronomical unit away from our star where we are sitting. If you go to an M-dwarf, it will be fairly close to the star. And if it's really close, that means you get very sensitive to any kind of action going on the surface of the star. So we know we have solar winds. We see them disrupting us then and then, even though we're sitting this far away. If you're sitting closer in than Mercury, you're going to get a lot more disruptions. So that's something people are thinking about because it seems like these small stars are extra sort of prevalent in hosting potentially habitable planets. The most famous system is the TRAPPIST-1 system, because it has 7 of these Earth-like planets around it, and 3 of them, so the 3 sort of in-between ones, could all be habitable based on their surface temperature conditions. But as I said, because this is one of these like really small stars, if you were to take all these 7 planets and sort of place them in our solar system, this is where they would be. So this is Mercury, Venus, Earth, Mars. This is where the entire 7 planets, like Proxima b system would be. So you can imagine that it's pretty easy to get scorched if you have some solar or stellar activity if you're sitting right there. So it is a question of how often, like these kind of planets, even if they have the right temperature for liquid water, how often would this kind of artist impression, showing some of the other TRAPPIST planets in the background, actually be true? Now, we saw Monday that water is actually very abundant in the galaxy, in the universe. So we would actually expect them to have water delivered to them and maybe even form with some water, similar to how the Earth had water delivered to it. There's no reason to think they wouldn't have it as well. The question is whether they can hold on to it with all this stellar activity going on. And the only way to really find out is going to be to do spectroscopy of the atmospheres of these planets. So spectroscopy, is simply making use of the fact that when you get down to the smallest level, quantum mechanics take over, which means that all changes in energy inside of a molecule or atom happens in quantized steps, which means that a molecule like water will only absorb and emit light at very specific wavelengths. And that's something that we can observe if we have very good telescopes and therefore tell if there is water there or not. So we're not there yet for these small planets, but we actually will be in the coming 5 to 10 years. But I think it's good here to sort of briefly pause and just remind ourselves why would we care so much about water? Why would we define, what is a habitable planet based on water? Seems, terribly Earth-centric of us. It actually doesn't come so much from, here on Earth, obviously, all life requires water. It's part of the very basic processes. But that is not really the reason why water is being obsessed about so much. It really has a lot more to do with the chemistry that we think preceded life. If you want to have a rich chemistry happen, you need to bring a lot of different things into the same solution. And water happens to be an incredibly rich solvent in the kind of things it can dissolve. If you want to dissolve things like salt, metals, that is actually quite difficult in most organic solvents, for example, while the polarity of water allow you to do it. So you can have a lot more reactions happening in water. That together with it, it's one of the few solvents that we think is abundant enough that you can bring enough of it to a planet to really act as sort of a planet-wide solution, are the main reasons why we focus our attention on these temperate planets. Doesn't mean that we sort of rule out that life can occur under any other conditions, but it does mean we think it's the most probable that if we find life elsewhere, it will also have arisen in a water-like environment. The other thing, though, that we want to ask ourselves then is water enough? What else would we need to say that the planet could develop life? And for that, I want to switch gear a little bit and think about what we think happened here on Earth, or what is a possible pathway, anyway, here on Earth. So if you look back on the history of the Earth, it looks something like this. This one is like sort of accurate, but it was the most colorful image that I could find, so we will work with it. If we go back, so the Earth formed, so this is correct, the Earth formed around 4.6 billion years ago together with the Sun. The first few 100 million years of the Earth's lifetime would not have been very conducive to life. It formed pretty hot, so you're not going to have a lot of, lava life, but you're not going to have a lot of things happening in the first, at least sort of tens of million years as the Earth is cooling down. And then sort of 100 million years into Earth's lifetime, even if by then had started to cool down enough, we had this catastrophic giant impact. The Mars-like body hit the Earth, and this is where the Moon-Earth system comes from. So whatever existed there in terms of life, water, chemistry, what have you, would have gotten wiped out by this impact. The next sort of few 100 million years ago, we had a lot of smaller impacts. most people think that a large fraction of our water was delivered to the Earth in these hundreds of millions of years that came after this like one big impact. You can think about this like basically comet and asteroid-like bodies impacting the Earth. Now, very soon after this, the moon creating impact and these sort of like smaller impacts, the first signs of life are claimed. Now, if we look, which is what's here, these sort of, there are different kinds of fossils of bacteria that people start claiming right around this sort of 3.8 to 3.5 billion years ago. Now, these are controversial claims. Bacteria does not leave the best kind of fossils, as you can imagine, that this is not your traditional, nice hard-shelled animal kind of fossil, which don't show up until like 500 million years ago. So we have this other 3 billion years where people are claiming they're seeing signs of life. Bacteria, though, can form these kind of mats that can become incorporated into minerals and leave a kind of fossil. But these look sometimes a little bit like, a rock formation. So people do argue whether they are actual fossils of life or not. Where you get the really sort of uncontroversial first signs of life is closer to like 3.2 billion years ago, when basically the field agrees that by then you are really seeing the remnants of something living. So what we can say for sure is that within a billion years, we did develop some sort of single cellular life. And it might have been as soon as 100 million years after the Earth became habitable. Now, something must have preceded this first life form, whenever it happened. As I said, somewhere around that sort of 3.5 to 4 billion years ago, very likely. So the scenario that people have come up with is something like this. So going sort of backwards. So if we take the most common sort of consensus view, that was about 3.6, 3.5 billion years ago, we have our last universal common ancestor. This does not mean the first life form. This just means that it's the life which we can trace back all current life to. There might have been initial different strands of life developed on the Earth. And this is where they put also around sort of 3.6 billion years ago, because we have no idea when that happened. Today, all life is DNA and protein based. So that's something that we must have developed around this time. People speculate that this was preceded by an RNA-based word instead of a DNA-based one. The reason for that is that RNA, if you have RNA, you can do a lot of things without extra proteins. So otherwise it's a question, did the DNA or the proteins come first? Did they come together? How can you get so much complexity at the same time? But RNA actually has the functionality both of storing information and of catalyzing some specific reactions which are needed for metabolism. This RNA word must have been preceded by something that provided the building blocks of the RNA. So this is pre-RNA word. This pre-RNA is a very complex, but potentially having some traces of sort of Darwinian evolution to it, but still a purely chemical word. Must have been preceded by chemistry that built the building blocks of RNA, which in its turn must have been preceded by the delivery of these basic organic chemistry building blocks to the Earth. So that's the sort of backwards history that people imagine. Now, what I want to think about is the chemistry part of that, which would be these sort of middle steps. Like how could we get from here and these sort of basic building blocks up towards the RNA word. And I guess I should have shown this one before. So the reason I said the RNA, RNA word isn't attractive, though not at all an exclusively favored hypothesis, is that you get sort of metabolism, reproduction, and information storage with a single kind of molecule. So you don't need a bunch of different, more complex molecules coming together. Now, so how could you like what are the individual steps in a bit more detail to get there, to get to these strands of RNA that would have to somehow be worked out as the Earth develops? Well, the first is just to form, as I said, these sort of building blocks of the RNA. And these on their own are pretty complex. I mean, it's not that easy to, if you have a soup of, let's say, some very simple organic molecules that we find in space, maybe methanol, ammonia, methane, to then go from there to sort of exclusively form the right kind of building blocks of RNA is not a trivial step on its own. So you have to go to there to then start them sort of starting to randomly put themselves together into small strands of RNA. Then there must be some way that chemical process comes under some pressure to push in one direction versus another. So basically what people are imagining is Darwinian evolution, but for chemistry. I mean, we're really not talking about living things at this point. If this is efficient enough, you might start building up strands that are long enough that they can start to copy themselves. They can start to catalyze their own sort of reproduction and start copying themselves. And the ones that copy themselves the most efficiently will be the ones that, take over their local environments. At this point, we're really thinking about sort of pre-Darwinian evolution. And that's what they have here. You get some sort of natural selection, if we can think about that without living things. And if you also, at the same time, develop some sort of compartmentalization, so think about it as a cell, but before you have proper cells, you might get something that has the basic functionalities that we associate with life, even though it's not all the way there in terms of being the kind of stable, reproducing life forms that we have today. Now, each of these steps, none of these steps have been figured out in a conclusive way. So I guess this is number one. We don't know if this actually works. But, and this is an important but, there have also been progress on sort of getting closer to closing some of these gaps over the past few years. So there is both progress and a lot of uncertainty at the same time. So people who say that, we know that we can go from this sort of very simple chemistry all the way to life, are either not appreciating where the field is standing or they're trying to push an agenda. I think we can, most of the time, I think it is simply just a misplaced belief in how far science has advanced here. This is still a field that is very much developing, where people hope they will be able to figure out all these steps, but it's not something that we know for sure. The one step that I think in media receives the most attention, even though in some sense it is the simplest one to figure out, is this first step. So how do you get from this sort of basic soup of chemicals into the building blocks of RNA and proteins and cells? This is an important step, obviously. You're not going to get further if you get from there. But I guess I just want to repeat myself that just because you get from here to here, which is what I'm going to talk about next, doesn't mean that you have figured out how to go all the way to here. And that these are probably actually more difficult to figure out. There are three sort of main ideas of where you could have had these first steps happening on Earth. The classical one is that you have some sort of discharge. So this is the Miller experiment kind of idea, where you have a soup of chemicals that you get into the atmosphere, you break them apart with a discharge, and then you get the chemistry, you form this soup of prebiotic molecules, like including amino acids and sugars and things that go into nucleotides that go into RNA. The problem with this experiment and why it's generally not that favored anymore is that the soup that you form just has a million things to it. So there's no reason why you should go from having a million things to nature selecting like 20 molecules to work with. That just seems like then the next few steps are going to be very difficult if you have that very unspecified soup. The other very popular hypotheses are these hydrothermal vents. So these are hot vents, volcanic vents that are in the ocean. They are popular because you get this source of energy, you get a lot of nutrients coming out, which before you can sort of really metabolize well, it might be good to have a lot of these, getting those from nature. And then the final one is these shallow impact lakes and other lakes where you get the energy from UV radiation. And you also can get a lot of nutrients sort of just like seeping out of the rock, basically. So just one, I guess, more close-up on the hydrothermal vents. So this is something what people imagine is you have these very porous structures where you get sort of pre-compartmentalized things, so that's good. You have this source of energy, that's good. You have lots of nutrients, that's good. A lot of the field would say that this is probably where it happened. However, so far, sort of those different steps that I showed have not really been quantified, any of them. So it's a very qualitative picture, I would say, even though there are many attractive features about these hydrothermal vents. Where most of the quantitative work has been in the past few years is instead in this sort of shallow lake scenario where you have UV light as your main source of energy. And then you have sort of day-night cycles where during the day you break things apart, and during the night you can put them together into interesting ways. And the reason that there's been some focus on this scenario, this sort of shallow lake, which is also what Darwin actually suggested, the pond, Darwin's pond. Why this one is sort of back in force is that when some very talented chemists have tried to figure out what would the chemistry look like in these ponds, what they get is something that at first sight looks scary. I mean, there are many, and I'm not going to go through this in any way, many chemical, networks and equations, but what is actually very simple compared to what you get in the Miller experiments. So when they try to simulate these kind of lake experiments, they do get a lot of, for example, the amino acids and the nucleotides and some cell membrane molecules, and they don't get that much else. So they get a much cleaner sort of production of the molecules that it seems like life today is using, which is an indication that this might actually be where life originated, because there seems to be that more direct connection between the chemistry in life today and the chemistry that they actually see. So this is going to be the one that I want to just have in the back of our head. And instead of that chemical reaction network, this is what I would like to have you to have in the back of your head as we go back to our exoplanets. So what do they need to get this chemistry to work? They really need three things. They need it to be UV light. This is going to be what gives the energy to drives the chemistry in different, interesting directions. They need HCN, so hydrogen cyanide. Not so good for life today, but very good to get it started. And they need some source of sulfur. I mean, those are basically apart from that, you can actually have many different things going on if you have those three ingredients. And with those ingredients, they can really form, and as I said, not much else, but they do form things like the amino acids, the nucleotides, some other molecules that it seems like nature has been using for an awful long time. So we can then ask, especially this hydrogen cyanide, which is so important, we can ask, did this kind of organic molecule, is it likely to also exist on other planets? Like the same kind of chemistry we had on early Earth, is it likely we will see it in exoplanets? As I said, we can't yet do spectroscopy on the planets we would like to do. So we're going to have to answer this question by thinking about where the planets formed and their sort of formation environment. And where planets formed, we looked at that Monday, are in these disks of dust and gas around young stars. So we're now going to look at the chemistry of these disks, what they look like. And the tool, just like before, is going to be this ALMA telescope, which allows us to look at molecular rotations, the spectra of molecular rotations. And I'll come back to that in a second. But the bottom line is that on Monday, I showed you that we can use the ALMA telescope to take pictures of these disks where planets are currently forming. You remember they had these, lanes that planets are carving out. What is amazing is that we can also take pictures of the chemistry in these disks. I think a more, common way that we think about taking chemical pictures is like a brain scan. When you slice up the brain, you see the different colors corresponding to different processes going on. It's a little bit similar to what we do here, that we try to take pictures of where molecules are located in these kind of disks. And the way we do it, I said, is out on microwave wavelengths. So ALMA operates at microwave lengths, same, kind of electromagnetic waves as used to boil water, which works because you actually excite the rotations and vibrations of water. So at microwave lengths, we get two kinds of light emerging from these disks. One is just thermal emission. So this is just, these disks are cold. If you looked at us, thermal emission from us, it would be at infrared wavelengths. Because these disks are cold, thermal emission comes more at these microwave lengths. So if you integrate all the light that you get, you will get an image like this of the structure of the disk. But then superimposed on this sort of continuum of thermal emission, you will see spikes that are due to spectral lines that comes from different molecules. At these wavelengths, they come from molecules spinning up and spinning down, which is also done in a quantized way, just as the more common electrons moving up and down, which is why you see the sun, like absorption lines in the sun, for example. Here it is because molecules are spinning up and down. And we can isolate the light from just a single one of those spectral lines and take a picture of that, and we can get the distribution like this, which is for a particular molecule, how it's distributed in this disk. So we can do that for HCN, our molecule we wanted to see if it's commonly around and where it is. And this shows a bunch of different disks up here, and then the HCN in the disks in the second row. And the bottom line is that hydrogen cyanide, HCN, is almost always there. It is a very common molecule in these disks. So it seems like the kind of sort of HCN-rich environment that we emerged in is probably quite common also for other planets. We can actually see more complex versions in the same family. So you can add a methyl group, or you can add just some larger chemical groups to this CN, the cyanide part. We see those molecules as well in most disks we look at. We also see them in comets, and we actually see them in similar proportions in comets and in these disks, which would suggest that the chemical environment that exoplanets emerge in is actually quite similar to the chemical environment that we emerged in. So the bottom line is that hydrogen cyanide and other organic molecules are abundant at these early stages of planet formation. So that seems like good news, but I do, want to emphasize that we are going to need some more direct tests to see how much of them actually gets delivered to planets and how much there are. And the only way to do that is for planets that are far away, so we can't visit them, is to look at their atmospheres, which is what we can access spectroscopically. So the way that we're imagining doing that, at least over the coming decade, is using the same transit method that we use to detect the planets, but now to split up the light that we see blocked out by the planet into different wavelengths. And then the size of the atmosphere will vary dependent on the wavelength we're looking at, because if you have a molecule that is absorbing, let's say you're looking right where water is absorbing, you're going to have more light blocked out than you would expect. So if you're looking at the place in the spectra where there's nothing in the atmosphere that's absorbing, you're only going to get light blocked out that corresponds to the solid planet. But if you're looking at water or oxygen, you're going to see this extra blockage at the right wavelengths as the planet passes in front of the sun. And from that, you can reconstruct a spectra, and from that, you can reconstruct what the abundances are of things like water, oxygen, maybe even hydrogen cyanide in the atmosphere. So there's a new telescope that's coming online, hopefully. It's scheduled to launch in 2021. It was scheduled to launch in 2018 and in 2015. So we're hoping this time it will actually go as, I don't know, it's a wonderful telescope. So I know I want you to think that your taxpayers are not going to a good place, but let's say when they did the shake test a couple of years ago, which, you shoot up a telescope into space, it's going to shake a little bit. So they did a little shake test, and sort of some screws and things started falling off. And then they sort of put back all the screws, but they were sort of left with a handful that they didn't know where they were. It's made IKEA furniture kind of moment. So they decided they had to take it apart a bit and put it back together, and that's basically what the delay is about. But it's going to be awesome when it flies. And what this telescope is going to give us is access to some weird habitable planets or temperate planets. So basically a couple of planets that are sitting around these M dwarfs, for example, that are very, very close to their M dwarfs. So we don't know if these are actually habitable because they can get scorched by their sun, but that's what we're going for in the next few years, because that's what we can do basically with the next generation of telescopes. It's James Webb Space Telescope. So it's the successor of Hubble, is the way to think about it. It's just much bigger, which makes it harder to, it's going to be, it's going to be a terrible, actually 6 months probably from when they launch it to when it starts, because they decided to not have a camera on there, so we're actually not going to know if things work as they should. And this whole thing is folded up, think like origami, it's sort of folded up to fit into the tube of the telescope, right? And then it's slowly going to unfold in some perfect way, and we wouldn't know if it works until we can start asking it to send back signals and send back data. So it's going to be a long, long wait. Now, if we want to get Earth-like atmospheres, and this is what the Earth atmosphere would look like from afar, together with that of Mars and the Moon. If we want to look at Earth-like planets, so Earth-like planets around sun-like stars, we're still probably a couple of decades away from that. We're going to need a set of telescopes that's not yet planned to do that. People have ideas, and there are sort of preliminary plans, but there's nothing that has been decided on that's going to that would be needed to do that. So I'm hopeful, because this is such a existential question, that this is actually something that will get funded. But from sort of inception to launch, it's a typical sort of 20-year timescale. So we're talking about sort of 20 years before we can start going after the planets that we think for sure would provide some constraints on whether we are living in a living cosmos or not. These are all in the end going to be indirect measurements of whether there is life on these planets or not, though. We can make sort of probability plots of if you find oxygen and methane in an atmosphere, we don't know any process, any non-living process that could produce that. But if you find just oxygen, we do know of non-living processes that could produce that. And maybe we have missed something. So just because we find oxygen and methane, we can say, okay, this is looking really good and interesting, but we can't say with 100% certainty that there's life on that planet. To actually be able to say for sure that there is life, you're probably going to have to do one out of two things. One is to visit, which for most of these planets, even the most nearby ones, is a very difficult thing to do, even as technology hopefully develops and we can do things much faster. The other is to start taking proper images of them. If you have a single dot of the Earth and you get single spectra, I said you could come up with scenarios where this is not a living planet. But if you start seeing things like this, especially if you start seeing sort of combination of green and blue and like seasons and how things change over time, I think then even the worst skeptic would say that this is a living planet. However, to do that, to even do something like this, fairly pixelated, but you should be able to pick out, blue and green changing over time, would require a telescope that's 150 kilometers. This is not something that is, so the biggest telescopes that we're right now building for $1 billion each is, here on Earth are 30 meters. The ones that are going into space are much smaller than that. They're 6 to 8 meters, the biggest ones, and that costs about $10 billion. 150 kilometers which totally worth it, by the way. Don't be scared by the numbers. These are remember, existential questions, civilizational questions. We have spent much more money on other things. But we just don't know how we would go about building this kind of telescope. It clearly wouldn't be a single dish. It would have to be many little dishes that are somehow operating together. But exactly how we don't know exactly what we would do here. And that's where I put more sort of, century time scale. But it's not something that's physically impossible. But it is a technological problem. I do, I guess, want to make one pitch for that. There are places, though, we could go to if we want to find out the likelihood that there is life elsewhere, having even one more detection of life that arose independently from that of the Earth would very much change our sort of probability scales, right? From totally unconstrained to actually fairly constrained. So there are places we can go to in the solar system which we have not explored. If all we think it takes an exoplanet to be a potentially habitable place is access to liquid water and access to hydrogen cyanide and other organics, there are actually several other bodies in the solar system that fulfill those conditions. One of them, which is my favorite, is Enceladus. Enceladus is a tiny moon around Saturn, but it has this three very nice features to it. One is that it has a liquid ocean under its icy crust. The reason we know it has a liquid ocean is because it actually spews out some of that water into space. So it has these cracks on its south pole, and there's a constant plume of water that is going out into space from there, which has been detected. And here you can just see the images, but also we have had instruments flying through it that was part of the Cassini mission, which was mapping out Saturn and a much bigger moon, Titan. But they also went through the plume, and it is mainly water. So that's one good thing. Another good thing is that it's very likely that this water is rich in organics, including hydrogen cyanide. The reason for that is that this moon formed roughly where comets formed. And we know comets, in addition to having a lot of water ice, they also do have a lot of organic ices, including hydrogen cyanide. So it's very likely this one formed rich in exactly the organics we want as well. And finally, it is very nicely just like putting it out into space, which means you don't have to go and drilling. You could go and scoop things up, basically. It's not that easy, but it's not that hard. And it's crazy to me that we're not doing this. We're talking about expensive missions, of course, but here we actually have in our backyard, the possibility to answer the question of whether life is something that emerges very easily or not. There's some very basic conditions fulfilled here, but they're still very different compared to the early Earth. So I'm just saying, we should go to Enceladus. But with that, so where are we? So from a scientific point of view, so there are many planets that fulfill the sort of basic conditions for making them habitable. That is, that they're temperate, they likely have access to water, and they likely have access to sort of the right kind of organic molecules. And with many, I think we can, I threw some numbers out through this presentation, so let's just bring them together. There's if we want to be very we want to be very narrow-minded in some sense. What is the living planets? We say we only care about stars like our own. We know that that's been a good star for producing life here on Earth, and we want an Earth-like planet in the habitable zone around that. So, on the order of a couple of % of sun-like stars have something like the Earth around it. On the order of, depends what you mean with sun-like star, but say about 10% of stars in our galaxy are sun-like. They have sort of similar stabilities and spectra and all that, which means that around 1 in 1,000 of the stars in the galaxies would have something like an Earth-like, sun-Earth-like kind of system. There are around 100 billion stars in the galaxy. So 100 billion divided by 1,000 is 100 million. So that would get us to, in our galaxy alone, which is realistically the kind of planets we could sort of see something in, and if there is intelligent life, eventually communicate with. So we have about 100 million of those. So that's a lot. I mean, that's, by any sort of factor, that's a lot. And we were talking about that in addition to having sort of these basic physical conditions, a large proportion of them are likely chemically habitable as well. Even if we know we drop a factor of 10 there, that still gives us a lot of millions of planets in our galaxy. What we don't know is how easy it is to get from having those basic conditions, going through these different steps on towards biological life. And that means that we're not really in a position to say what the probability is that there is life out there, even very basic life. If you talk to most of my colleagues, their assumption is that this is not so hard to develop life. And I think their basic intuition is going back to sort of some of the arguments from the Galileo affair, which is that or not really Galileo, but things that emerged after him, which is that we are not really in a special place in the universe. For most, I think, scientists, it doesn't really make sense that something would only happen here, that it's that somehow the conditions were so special here and that they don't occur at other places pretty regularly as well. But I think it's important to keep in mind that it is an intuition. It's not something that is backed up by sort of scientific facts at this point. Now, I hope they're right. And I said, I remain sort of agnostic because I think it would be awesome to have life elsewhere, and I'll come back to that. But that's where we stand scientifically. And finding life even at one other place would totally change those probabilities, even if the error bars would be big, into sort of like non-existent, into something that's actually fairly constraining. So even if we're just considering like the fact that there are exoplanets out there, to go back to sort of the cosmos, so what does that say about our place in the universe? The fact that our solar system is just one of many words there. I'm not sure that it's saying anything negative. I can't think of anything that's bad about that. Around stars, there are this potential, unexpected and really exciting new words emerging. It seems to me that exoplanets is exactly the kind of thing that you would sort of expect God to do. It's sort of something that fits in very well with the laws of nature as we know them. But it still was something we couldn't really predict, until we actually saw it, and especially how diverse kind of systems that we see. I think what we expected at best was to see sort of little copies of our solar system. And I think this is just another example of the cosmos being much more interesting and much more beautiful than if we had made it, what we would have done. So, Deo gratias and all that. But I think when it's start getting interesting and where it might affect our cosmology and our place in the universe even more is if we start thinking about, is this a living cosmos in the sense that life is abundant and common? Or is it one where it's rare and maybe even only exists at one place? In the former place, this would be sort of a universe of gardens, right? where there is an overabundance, sort of a creative, almost overabundance of life wherever you look. And I think there is something like an intuition for many Christians to say that that is probably what God would do. He seems to be someone who really takes a lot of joy in creation. I mean, that's the sense you get, I think, both from scriptures and from the book of nature, that this is just sort of a beautiful, joyful thing that he does. And the universe is so big, wouldn't he have painted the rest of the universe with different colors, not just this place? However, as I said, we don't know if that is the case. It might be that he created this entire universe just for us. And the beauty that we see is actually there for us. And that we are, in some sense, the ark, carrying all living beings through space and time. And I mean, there is a strange and almost very solemn beauty about that, thought as well. And I'm very excited to see which it turns out to be, because I do think it says something about the personality, if I can put it that way, about God, which one of the universes we end up inhabiting. Then I think, though, there is no sort of conflict between any sort of theological understanding and which one of those comes about. That is more we get to know God the Creator a little bit better. I think where sort of the nervousness comes in is when thinking about whether some of these planets are just not inhabited by some sort of creatures, but by rational creatures as ourselves. As I said, there are two sort of potential tensions there. One is, and this is something you hear often from the new atheists, who first of all assume that life develops everywhere, that all those steps that I just told you are actually pretty hard, and we don't know if you're going to figure them out, that, science, and then it will all be figured out. And since obviously it will all be figured out and happens all the time, that means there will also, and we are just, a byproduct of evolution, obviously rational beings will happen everywhere. And because of rational beings everywhere, why would God become one of us? I mean, that's pretty much the argument. And I'm not even, I think, misrepresenting it. That I think is the sort of the gist of the argument. So how special are we if there are other rational beings out there? If there are other beings that have been created in the image of God, which is what we are taught that we are. Well, I guess the first thing I would bring up is that we already know that there are other creatures being created in the image of God, and we call them angels because they don't have bodies; they're just pure intelligences. And this has in no way interfered with our special relationship with God. On the contrary, it's been something that has often strengthened our relationship with him through the different ways he has used us and them to communicate with one another. That alone, I think, should give some comfort that God's sort of generosity to others does not diminish his generosity to us, right? So I think that one can be sort of a psychological problem, but I can't really think of that as sort of a theological problem, that he would create other things in his own image, beyond the angels and beyond us. I think the real tension is that it comes with the incarnation. We believe that not just we, but in some sense the whole creation were redeemed through the incarnation, right? I think that's the most straightforward reading of the scriptures. So this raises the question, how would these other rational beings be redeemed? Were they redeemed? I guess assuming that they fell. And I guess here, if you have read C.S. Lewis' space trilogy, it's not obvious that they would have fallen, right? We had a choice and we fell. It's not obvious that others would have taken the same choice. On the other hand, it seems to have taken us about 2 seconds to fall, which to me would suggest that this is, and we know that a portion of the angels fell as well, that this seems like when creatures are given free choice, it seems unfortunately like a lot of the time, a lot of them choose to look away from God. So assuming that there are indeed fallen rational beings out there, are they redeemed through the one incarnation of Jesus of Nazareth? Or could there be other incarnations? Now you can answer this both metaphysically and by scripture, of course. So let's start with the metaphysics. Thomas, St. Thomas Aquinas is a good place to go, and luckily he actually does answer these questions. So, Tertia Pars, question 4, article 1, is it basically what kind of being would it be proper for God to become incarnate in? Is what this question asks. And he makes the argument that the only kind of being that would be proper would be a rational being, like someone who has been created in the image of God through his or her rationality. So it means that we're talking about alien life forms that are not rational beings. That is not where we're going to need to worry about the incarnation, but that it is only proper for God to become incarnate in a being such like ourselves. So, and there's basically two things it has to be rational, but it also has to be, Thomas thinks, savable. So it would not really be proper. I mean, you can't really talk about God becoming incarnate as an angel, because, no carne. But it also, in some sense, wouldn't be proper because they have a one-time choice, while we, luckily, have many. And therefore, the incarnation is something that can redeem us. Now, the second thing that Thomas asks, which directly gets to our question, is, could incarnation happen more than once? And could the other persons of the Trinity become incarnate? He says absolutely yes. I mean, God did not lose his power to become incarnate because he did it once. While it seems more proper that the Son becomes incarnate, it is not like the Spirit doesn't have the power to become incarnate. All powers belong to all persons, all divine powers belong to all persons of the Trinity. So metaphysically, I think there is the option for, in some sense, multiple incarnations. But we don't just have metaphysics, we have revelation as well. And I think if you do look into the scriptures, and there's a wonderful book that goes through both the metaphysics and sort of the evidence, if you're going to call it like that, from scripture and from church teaching, which is Marie George, Christianity and Extraterrestrials. I mean, I don't necessarily agree with her conclusions, but she lays it out so beautifully, clear and logical. This is just a great book. And if we follow her and her sort of walking through what the scriptures is saying, I mean, any sort of straightforward reading of the Gospels and of Paul would suggest that the incarnation is really a one-time event, which I think also fits in some sense with most of our intuitions, that this is such a momentous kind of thing that God would step into creation, that it seems more fitting that it would happen once. I said beyond that, Catholics have the extra, teaching of Mary's queenship as the mother of God. Are there, mothers of God? I guess the incarnation wouldn't have to be as a baby, born through a woman, but there are definitely tensions that develop there, but I think with any sort of straightforward reading of the scripture. But I mean, we have learned in the past that sometimes what seems like a straightforward reading is not always the intended reading, and there is no church teaching on this topic. So this is something you are totally allowed to, speculate about how to actually interpret. I mean, the Gospels were clearly, and the letters, the New Testament was clearly directed towards people here on earth. They're not really concerned about the potential rational beings at other places. And therefore, when they talk about the whole being redeemed, I would say you could make an argument, and other people have made the argument, that they are not interested in thinking about the whole outside of the earth. That their concern is with us here, and they will use the language that is sort of conveys that in the simplest possible way. But there is definitely tension there, and I think, interesting and fruitful tension. If you want to have your students figure out what is the theological, arguments for and against extraterrestrials, you might actually get them to look pretty carefully through some of Paul's letters, which might be a fun exercise. Now, I'm actually hoping that Marie George is totally wrong, and that this very straightforward reading, totally wrong in that she actually goes a step further and says, considering that we can't really have a second incarnation, it seems to her very unlikely that there is a second set of rational beings, even if in theory they could be redeemed and saved through Christ. It seems like the physical connection we have with Christ, that we are of sort of the same blood, that is actually something that matters. And depriving sort of other rational beings of that direct connection is something that doesn't really make sense to her, that they would be saved in sort of a more indirect way than we would, and that you would have to communicate that redemption to them through angels would be the preferred communication method, since we can't really hope to evangelize over hundreds of light years away. So she comes down and it's probably they don't exist when taking all this into account. Now, I tend to agree with her mind that the incarnation seems like it should be a one-time event, but I'm not so sure about the sort of second line of that argument, that because we get this sort of privileged sort of relationship with Christ, that sort of precludes them being saved still in a full way by Christ. I mean, to me, it actually seems like it's very much been the way God has worked with us here on earth, is to sort of start with one person or a very small group of people that get this privileged relationship with God, while the rest of humanity does not. Work with them, and then through them, communicate himself to the rest of the people who do not have the same sort of strong connection or initial connection to him. That definitely seems to be the case when you go from, from the Jews to the Gentiles, when you go from Christ, which was a single person living at a single time. I mean, think about the difference between the relationship the apostles had to him compared to us. And yet we are saved through this beautiful relationship. So to me, it's not necessary to jump from one to the other there, and that's where I disagree with her. I actually would really very much hope that you one day run into some extraterrestrial, intelligent, or rational beings. I think, imagine the comparative religion you could do when you get to see how God has chosen to reveal himself to this alien race that is still of the same species as ourselves. And with that, I will stop and take questions.
Okay. So the worst thing in the world is when a facilitator of a seminar asks a question before the participants, but I have a very quick one. So one interesting distinction that Thomas makes with respect to the incarnation and rationality is that he links, on the one hand, rationality and our materiality. So angels, strictly speaking, are not. And he even cites Gregory the Great, who says that angels uses them sort of adjectively as being rational, but only as an analogy is how he understands it. So on the one hand, you could say that actually seems to kind of amp up the possibility of thinking through an incarnation of material extraterrestrial life. And on the other hand, then Thomas does himself say any person of the Trinity could become incarnate. So I wonder what you thought about that. I wonder what you thought about the bracketing of non-material being with respect to rationality. And there's a suitability of maybe the Word being incarnate as a human being. Could you say the same thing is there a suitability of some other life form for another person of the Trinity, and how would that logic go in your mind? It's a crappy question, but it's a good question. But it's crappy of me to ask it on the.
It somehow seems like a question more appropriate for a theologian than an astronomer.
But it would be less interestingly answered.
It is an interesting question in a sense. I think also that I think there's something in us when we think about the Son becoming incarnate, that it makes a lot of sense that we have also the image on earth with him having a father and a mother, that it becomes extra appropriate that he's somehow born and raised in a family. And that also brings in Mary as the problem, in the sense that we really do acknowledge her as the mother of God, and I don't think we would want to get into a situation where we have mothers of God. But if you imagine the Spirit becoming incarnate instead, it is not obvious that it would be in some way proper that he becomes incarnate as a child, for example. That you might have an incarnation into something like a grown person within that species without in any way violating sort of propriety. And that, I think, would be an interesting way to get around some of the otherwise issues. So I don't know if that was where you were going.
That's awesome.
Yeah.
All right. Questions for our presenter?
I will admit it's not so much a question, but just a comment. And I wanted to say thank you for your approach to this as a person, as a scientist and a woman of faith, because I think sitting back, first of all, as a theologian, this science was so far over my head I couldn't even figure out what question to formulate. But I think the animosity that can exist between faith and science could be so lessened if so many more people on both sides of the argument did what you did, which was to say, as a scientist, sometimes we don't know, and as a theologian, sometimes something else is a possibility. And if we were more willing to be open like that in so many things, but in this dialogue specifically, we would be better off.
Yeah, and it turns out humility, generally a good thing, right? So I totally agree. Difficult to practice, but...
Mine's a little bit of a comment and then a question. First of all, I also am on the theology side of things, and this was amazing because I feel like you really did bring it down to a level that I could comprehend. So I truly appreciate you for doing that, and I compliment you as a teacher for being able to.
Coming from another teacher is it's a big one.
But I wonder if you could speak just a minute on the idea, if any of the encounters you've had with other scientists who maybe agnostic or atheist, ever feel like by saying like extraterrestrials could not exist, that is limiting God in a sense? Or because I think some people say, particularly when people approach me, it's like, well, if we discovered, aliens, that would mean that everything we know about God, and I think like, well, how could you feel that way? To me, that you are already limiting God in that.
Yeah, I don't think as a theologian that you would want to say that there's no way that aliens could exist. I think what Marie George is doing, though, is trying to think about sort of through what is likely based on her best understanding, like metaphysical and theological understanding. That I think is totally legit. And she does not rule it out. She says, but in her, the best analysis she can make, it's not very probable. And I think that just as I think a scientist is, as I did sort of in the first part of the talk, you say with the data that we have right now points toward that the basic ingredients for life are there, and we are sort of, seems like we're solving some of these like problems we had with how you can go from chemistry to biology. So most of our intuition points towards there being life elsewhere, even though we don't know for sure. So I think both are legit, but I think it would be very bad in general, and in this case in particular, to tie your theology to sort of a specific scientific theory. In this case, that there are no other life forms, or at least no other intelligent life forms. But I think speculating about it, coming to your best opinion from a theological point of view, I think that's good, because that sort of sharpens our minds, right, in thinking about it. But yes, I think I said it Monday, but we've been there, done that, in some sense of saying that the only way that the only sort of cosmology that Scripture allows is this one, and then it turned out to be the wrong one, and that probably set the church science relations back for 200 years. That's so like those kind of mistakes cost, and I totally agree. We don't want to go there, but I said Mary George's book is great, even though I disagree with the final chapter. That's just because she lays out her reasoning so well, which I think makes it impossible, which is why I like people actually pushing the envelope a bit. That forced me to think about why I actually don't agree with that last part, and forced me to think much more deeply about it, which I think is exactly how this kind of dialogue should do.
brother and then pass it over.
Actually, at the meeting I was just at, so I get most of my funding from the Simons Foundation that have this collaboration on the origins of life. And they have started with this little microphone, like stuffed cube that you just throw to one another. It's awesome, except that I can catch, but I can't throw for the life of me. So I ended up basically running between people.
Yeah, I've been to one of those conferences.
Yeah.
Thank you very much for your wonderful presentation. And I think on Monday I kind of asked a question around this topic, and what I see is there's a lot of explorations going on, a lot of speculations about whether there are other beings, whether rational or irrational, in other planets. I've also come across some commentaries that some of them are in movies, some are just in some Discovery channels, where some scientists are exploring the possibilities of habitability of other planets, just in case the Earth collapse. We can go there and start all over again. So, and the whole thing, I began to ask myself, why are we in this, why are human beings in this planet in the first place? And we all know that everything is passing away. At some point, everything will be gone. The scripture says there will be a new heaven and a new earth and all those things like that. But the idea of doing things that can deliberately destroy this planet, all this issue about emission and all those things, because of the possibility of another habitable planet for people to go and live and stuff like that. So that makes me to ask, why did God, or why did reality put us human beings in this planet with all the history that has happened, the history of salvation, you know? I don't know if you have something to say about that.
Yeah, well, I mean, we'll see, but I'll try. Well, so I think there are different ways to look at it. On the one hand, he also seemed to have focused a lot of his attention to a very specific part on the Earth, but then I think we're all very happy that, you know, people moved away and moved into different parts of the Earth. So it's sort of the whole Earth now today knows Christianity, even if it's not a whole Christian word. So I think the idea of sort of exploring and moving to new places and sort of bringing God into those new places is a good one. Obviously, there wouldn't be any sort of evangelization assumptions to do if you go to Mars. I mean, I think the assumption would be we'll go to planets where there are not other people or life forms and sort of try to colonize it in some sense. I think it's a beautiful thing to do, to try to explore also the other planets in the solar system and put people on them. Now, it's never really going to be, I think, a proper sort of backup. I think the Earth is always going to be precious because even to sustain sort of a small group of humans on Mars, even sort of attempts to terraform it is going to take a lot of effort. It's going to take, you know, thousands of years. It's never going to be stable the way that the Earth is stable as a place to live in. And I think Mars is the obvious next step. And it's very speculative once you start thinking about other planets. But that seems to me to be like a good idea and a beautiful thing to do. Not just, I think the Earth will remain precious, but there are things that could happen to the Earth that wouldn't really be of our doing. We have had large impacts before. Maybe we will develop technology to, you know, not have those happen. I mean, NASA has, one of my former students works at the, you know, Earth Defense Program, which is set up there to, you know, localize potentially like really dangerous asteroids and comets coming in and hitting the Earth and figuring out ways to mitigate. You know, think, you know, Bruce Willis. But there are like it is not as if, like, I can't see anything bad with having sort of a fraction of humanity like moving on to different places, even as this continue to be our primary home. Yes, I'm not really answering your questions, but that's, I guess, my thoughts is that it doesn't really threaten the special gift that the earth is, which I think it clearly is, that this is the garden that God made for us, that we also try to push the boundaries with where technology can take us in terms of other places, really as far as we can.
Unfortunately, we're at the end of our time, and hopefully if you have lingering questions, you can talk to Professor Öberg before she leaves today. But let's give her a round of applause and thank her for her.